heart disease, we want this model to give them a low risk estimate. Value for p close to 0. That means the value for 1 minus p is going to be close to 1. So a good fitting model will be a model that gives us a value for L that's close to 1 when you multiply all those numbers, p's and 1 minus p's together, all of which are close to 1 if the model is fitting well. That means the log of this number is going to be close to the log of 1. The log of 1 is 0. So what we're rooting for here is a value for minus 2 log L that's small, close to 0. Now what we have here is if we look at the model that has only the intercept, the model that says everyone's log p over 1 minus p is just b0. In other words, the coefficient of male is 0. The coefficient of pax 1 is 0. The coefficient of pax 2 and pax 3 and pax 4 are 0. That means everyone gets the same estimated log odds of getting disease. Everyone gets the same b0 for their log odds. Everyone gets the same value for their odds. Everyone has the same value for risk, regardless of your sex, regardless of your smoking level. If you just fit the model, oops, the value for minus 2 log L for that model is 1350. So 1350 is how well the model would fit if you gave everyone the single risk. If you allowed everyone to have different risks depending on their sex and depending on their smoking habits, that model fits better. Well, how much better does it fit? Well, the minus 2 log L dropped from 1350 down to 1321. That's a drop of 29 points, 29.4. So that number 29.4 is a test of the overall fit of the model that has both sex and smoking in it. So this test here that says global null hypothesis, all the betas equal to 0. What this test statistic 29 is testing is whether sex and smoking as a set have any predictive ability. Because what it's comparing are two models. A model where everyone has the same risk versus a model where everyone has different risks depending on their sex and depending on their smoking habits. And if these models have roughly the same values for minus 2 log L, that means that the model with sex and with smoking in it is no better than the model without sex and smoking in it. So we use this test here with this test statistic 29.43 to answer the question, do the set of predictors smoking and sex together matter? Well, they matter if the minus 2 log L dropped by enough points. What drops by 29 points? Is that enough of an improvement? Well, the way we can determine that is by looking this value 29.4 up in a chi-square table with 4 degrees of freedom. We'll talk more about degrees of freedom a little bit later, but the reason it's 4 degrees of freedom is that this model with the intercepts and the covariates has a B0, a B1, a B2, a B3, and a B4 that have to be estimated. 5 things have to be estimated from this model. The intercept-only model has only the B0 term. So the difference between the model with the covariates and the model with just the intercept is the addition of 4 extra terms. 4 extra coefficients have to be estimated. That's what this test is addressing, whether the addition of those 4 extra coefficients improve the fit of the model. And the result is, yeah, you get a significantly improved fit, p-value less than 0.001. And now the question to ask yourself, from this one test, this global null hypothesis, can you tell me whether sex is an important risk factor when you control for smoking? Or can you tell me whether smoking is an important risk factor if you control for sex? And the answer is no. All you know is as a set, sex and smoking matter. As a set, they give you a significantly improved fit, p less than 0.001, when you add those 4 statistical variables, male, pax 1, pax 2, and pax 3. It might be that the improved fit is because male is important. It might be the improved fit is because pax 1, pax 2, and pax 3 is important. Or it might be that both are important. The point is you don't know because all this test is telling you is the importance of the fit of the overall model that has both sex and smoking in it. And if you were fitting this model to look at the effect of sex controlling for smoking, that's not the question you have in your mind. What you want to know, if that were your case, is how significant is the male coefficient, the B1 term, after you control for smoking. And so far, nothing on this slide is going to tell you that. But the next slide will. Because here's your fitted model. Here's your estimate for B0, minus 1.7799. Here's your estimate for B1, 0.6778. Here's your estimate for B2, B3, and B4, the coefficients of packs. Each of these estimates has a standard error. If we divide the estimate by the standard error, we get another test. This is a specific test. These tests are addressing the significance of just the coefficient of one of these predictors. So, for example, if we take the estimate for B1, the 0.6778, divided by its standard error, 0.6778 divided by 0.14 gives you a value of about 4.5. If you square that ratio, you get the number 20.93, corresponding to a p-value less than 0.0001. What this test statistic is measuring, what this chi-squared test is addressing, is a different hypothesis than what was on the previous slide. This test is addressing just the significance of the B1 term. It's asking, if you control for smoking, does sex matter? If you added male to a model but already had PAX1, PAX2, and PAX3, would that improve the fit? And the answer is yes. Males are significantly different in their risk estimates than women, even after you control for smoking. It's a highly significant risk factor. The fit of the model improves if you add sex to the model that already has smoking into it. And you can go one step further. You can take the coefficient of male, the 0.6778, and turn it into an odds ratio. Take e to the number 0.677, you get the number odds ratio 1.97. So you can conclude now that the odds of developing coronary heart disease for a male is almost twice as much as it is for a female after you're controlling for smoking, after you control for smoking as a categorical variable, and representing that as 3 indicator variables. And you can build a confidence interval around that odds ratio, going from about 1.5 up to about 2.6. Now, this confidence interval, and this test is significant for the B1 term, are impacted by this standard error value. So in about a half an hour or so, I'd like to talk more about standard errors and what that number really is representing. So far from this 2 pages of SAS printout, and there's more that I didn't show you, what we can conclude from the previous slide is that smoking and sex as a combined set significantly improve the risk of your model's ability to predict the risk of developing coronary heart disease. And more importantly, the purpose of this model was to control for confounding by smoking and look at the adjusted effect of males versus females on their risk of developing coronary heart disease. Male is a significant risk factor corresponding to an odds ratio of around 2. But this model is making an assumption. It's assuming the best way to control for smoking is to categorize it into packs, having values 0, 1, 2, and 3, and represent that variable in the model as by 3 indicator variables, PAX1, PAX2, and PAX3. Now what you should be thinking about is that the best way to control for confounding by smoking? To answer that question, let me show you one other model. Here's a model that includes a single term PAX in it. It doesn't include PAX1, PAX2, and PAX3. This is a model that's keeping PAX as a continuous confounder with 4 different values, 0, 1, 2, and 3. So what sort of assumptions are being made when you fit this model, which has PAX being treated as a continuous variable, versus the previous model that had PAX being represented by 3 indicator variables, PAX1, PAX2, and PAX3. Essentially, the previous model was categorizing PAX and treating it as a categorical variable. Here we're categorizing it as a 0, 1, 2, 3 variable, but we're not treating it as a categorical variable. We're treating it as a continuous variable. A person who smokes 2 packs a day gets a value of 2 for PAX. A person who smokes 3 gets a value of 3. A non-smoker gets a value of 0. A 1 pack a day smoker gets a value of 1. One of the questions we're going to be asking for is this a better way of controlling for confounding? Well, let's look at this output. We get the same minus 2 log L if we just fit the model with the intercept only. In other words, if B1 and B2 are both 0, everyone get the same intercept value B0. Everyone have the same risk of developing heart disease. That corresponds to a minus 2 log L of 1350. If we included male and smoking in this model, with smoking as a continuous variable, minus 2 log L drops down to 1324.